Okay, there you are. It's nice to see all of your smiling black boxes and names. Welcome back to MAC 1140 Pre-Calculus. Today we are going to finally talk about inverse functions. Just a quick heads up about a few things. My wife is about to have to use the bathroom, and our son, our baby, is going to be sitting in his little swing for a minute, but if he demands attention, I may have to hop up and take care of him. The other thing is that my dog Hamlet, who you may or may not have seen in the background here over the last few days, I don't know if I ever mentioned this, but he has a nasal tumor cancer that's in the last few days gotten much worse, and we're gonna have to put him down. So I'm waiting for some calls from vets, texts, things like that. And if those come in, I am going to take them. So I apologize in advance if any of those interruptions take place. Hopefully they won't. But just a heads up to you guys. With that out of the way, thank you, Hugo. I appreciate it. The truth of the matter is these cancers in dogs, Labradors especially in the nose, are usually very aggressive. And he was diagnosed, I think like 10 months ago. And usually they only last a few weeks. So as hard as it is to bear, I've gotten more time with him than I expected to. So I appreciate the compassion.
My dog went through the same. He lasted, I think, like was 2 months after it was diagnosed. So
sucks, man. Sucks.
Yeah.
I wonder, I've been like going through my head over and over again about what sort of environmental factors could have been relevant. And I wonder if it's not the pesticides that they sprayed on the lawn at the place I used to live, because he goes out and sniffs the ground. I'm sorry that you went through that. It's really rough. It is. So we have one section to cover today, which is a little bit less material than we normally have to cover. So we can kind of go in deep a little bit, which is good. The other thing is if there's a homework problem or two that's been driving you nuts, since today is our last class meeting before the test, we can talk a bit about that. Before we get into that, let's just do the let's say the 8th, right? 7, 8, 21. So today, we're going to talk about the test. We can take some homework questions. If you have a question from the quiz, we can talk about it a little bit, but I'm not going to solve the full problem. Cover inverse functions. The concept of a one-to-one function. And yeah, that's it. So this is section 2.8, which is the last section on the test. So while I'm kind of beginning to outline the rules and procedures for exam 1, if you want to take a look at the homework and see if there are any questions that you're dying to ask about, we can do that. But please also do pay attention to the phone. So exam 1, as we said last time, is next Monday, which is July 12th. And it's during class. This being a hybrid class, rather than a fully online class, we must do the tests during class time unless we've made arrangements otherwise. So what I'm about to say applies to anybody who's going to take the test with us. If you're taking the test with the DRC or in a testing center, something like that, then they'll be doing the proctoring. But here's how it's going to work. So first things first, the test is in Canvas. And it covers the sections from the text, from the syllabus. So like we said in our syllabus, 2-1, 2-2, 2-3, 2-4, 2-6, 2-7, and 2-8. So 2-5, 2-6, 7, and 2.8. Again, the quiz in WebAssign, you can kind of think of that as a proto-test, a pre-test kind of thing. Those are the level of difficulty questions that I intend to put on your test. Other details here, they're going to be true, false. And these are, there's going to be like 4 to 5 of these, and they're 4 points each. It's going to be multiple choice. Again, 4 to 5 of these, they're worth 6 points each. And there's going to be free response. It's going to be 6 to 8 of these, and they're worth 10 points each. The way the free response questions work, obviously you'll solve the problem. You'll write out your solution on your paper as you solve the problem. Then in Canvas, you'll type your final answer, just your final answer. These solve on paper. Type just the final answer. Then after the test, you'll scan and upload the written work. So the place you will be scanning and uploading that written work is in Canvas. I think we kind of talked through this a teensy bit on the first day of class, but here's the deal, right? You come in here to take the test. Obviously, it'll look a little bit different for you, but that's where you'll begin. Take the test there. After you go through all of the test questions, right? Making sure that as you solve the free response problems, you write out your work. After you finish the test and submit it, you're going to come to, where's my exam one written work? Right here, this separate assignment, and you will upload your scans of the written work. The credit for the free response problems comes from the written work. The typed final answer that you give is worth like 2 out of the 10 points. The other 8 out of the 10 points come from your written work. So it's important that your written work is legible and that the scan is readable, right? So look at your scans before you submit them. Some advice on how to get good scans. I'll share that with you in a minute. One other thing, do not forget to type your final answer in Canvas. If you just type answer on paper, I can't give you credit. Cannot. I need the final answer typed in Canvas and the written work. So that's in order to verify that the answer you typed is connected to your written work. I've seen various flavors of cheating. I'll describe to you the other things I do to try to get around or avoid that, but just please remember, right? Type your final answer. Forget to do that. People do that a lot, right? And it's understandable. I get it. Like you're going through, you just solve the problems, and you're like, I'm going to type the answers at the end, and then you run out of time. No bueno. Solve the problem, type the answer, then move to the next problem. Then when you're done with the test, scan and upload the written work. For the scanning, I suggest the app called Cam Scanner. It's free. It's available for Android and iPhone. But that, if you're on Android, I really strongly suggest that. Or if you're on iPhone, you can use the Notes app. I need the scans to be a PDF. So if you have another app you like more, by all means use it. Cam Scanner is just the best one I've found so far. I use Android. I don't have any experience with iPhones myself, but I've had other students in the past tell me that the Notes app is capable of this, and then those students have submitted beautiful scans. So I trust that it works well. If you try to take a picture, just a regular picture, a few bad things are going to happen. First, there won't be appropriate contrast. Second, the lighting often washes out or the angle is kind of shitty. So please pay attention to what you're doing. If you kind of hold your phone, if you kind of hold your phone right over the thing, I can cam scanner here, up here. Okay, here's the cam scanner app. Scoot this down. Start scanning. So, I know. So if you hold the phone like above the page, level, you'll get a good quality scan. If you hold it like off at an angle, or you're like sitting on your desk and you try to like do one of these, it's gonna come out bad. So please just do like the kind of obvious thing, hold your phone level, parallel to the surface that your paper is sitting on. Make sure you have decent light, and then make your scans. App is free, gives PDFs, gives really high quality, good contrast. It's the way to go. I ask that you do one problem per side of the page. So like one problem here, then flip over one problem. If your solution is really short and you can fit two easily on one page, that's okay, but don't clutter the page. Here, remember everything I put on the .cam should go in notes. Please write this down. Don't clutter the page. I suggest one problem per side. And that's a pretty strong suggestion. If you don't do that, it's not the end of the world, but for the love of God, make sure it's legible, right? Because again, this is your grade. I grade the work for the free response, and then I just match the final answer to the work. If the final answer matches the work and the work is good, then you get full credit. If the final answer matches the work and the work is bad, then I'm going to grade that work like I would any other test. If the final answer doesn't match the work on the page, then you get nada. The only way I can see that happening is if you were to cheat, write down, you work it on paper and then it doesn't come out right. So you pull up your second or third device and whip out photomath or something and type in what that gives you. I'm hip to that shit. I know what photomath output looks like. I know what integral calculator math output looks like. I know what Wolfram alpha output looks like. Please don't try any of that stuff. Like I said at the start of the semester, be honest with me, I'll work with you. So this is my advice for exam one, is of the rules and procedures. What else? I think I'm forgetting any questions about exam one. Oh, Proctor. Yeah, sorry, not done yet. So this is what's up with the test. This is how you do it. Proctoring for the test. I know this is a little long-winded, but please bear with me. There are two systems. First, honor lock. And if you've taken any math classes at Santa Fe over the last year, as COVID is going on, you're familiar with honor lock. If you're not familiar with Honor Lock, this is an extension for the Chrome browser. So you need to have Chrome installed on your laptop, your main device, and you need to install the Honor Lock extension. If you don't have it installed as you go to the test, it'll automatically take you to the page to install it. But please make sure Chrome and Honor Lock are up to date. Ainsley asks, rather pens or pencils? I recommend pencil, because you're doing math and you guys are learning, so odds are you're going to want to erase at some point. But it doesn't matter to me. If you prefer to work in pen, pen is fine. Again, just make sure the work is legible. So Honor Lock is an extension for Chrome. Make sure you've got Chrome installed. Make sure you've got Honor Lock installed. Make sure both are up to date. Both the extension and the browser require updates from time to time. Easiest way, if you don't know how to update the extension, just uninstall it and reinstall it. Chrome has its own automatic update system, so as long as you haven't been ignoring those, it'll be up to date. If you have been ignoring those, just Google how do I update Chrome. It's not that hard. The other system, Zoom, on your phone. So on your smartphone, like on Monday, I'm going to post a link to come to class like normal. You're going to join that Zoom meeting from your phone. So you need to install Zoom on your phone. And then you're going to take a mug or a coffee cup or something, set it on the side of your desk, your workspace, wherever, lean your phone up against it. I need to be able to see your hands. I need to be able to see your paper. I need to be able to see your lap. For the obvious reason that everybody these days has 3, 4 phones, tablets, things like that. And I just want to make sure there's nothing sketchy going on. This is the best way for us to ensure that, that you don't get roped into a honored conduct trial that you don't deserve to be in. Right? If you're doing the right thing, you're not cheating, then this is the easiest way for me to see that. So you'll need your laptop to take the test, or your desktop or whatever computer you use, and you're gonna need your phone. You're going to install Zoom on your phone. If you've never used Zoom on your phone, it's easy, but I would recommend installing it ahead of time and just making sure that you know what to do in there to sign in. Cams and mics stay on. The whole time. Everybody's going to go into their own breakout room. So Honor Lock will be recording your webcam. Honor Lock will be recording your screen. Zoom will be recording your desk, your hands, your lap. And I will be popping into your breakout rooms during the test, just asking you, how's it going? Do you have any questions? The same, as I would if it was an in-person class. I walk around, check up on you. If you need any help, if you're stuck on something, you can ask a question during the test. That's fine. In Zoom, that's how it's going to go. Questions about the proctoring?
I have a question.
Yeah, sure.
So with the when I take tests, I eat I have to have a snack or something. Is that okay?
Oh yeah, that's totally fine. I get it.
Okay, because I have to eat something to keep my brain.
Yeah, no,
yeah.
You're good.
Thank you.
I'll say one more thing about this before we move away. If you don't have a smartphone, I know that this is like a 1 in a million chance that a college student in 2021 doesn't have a smartphone. If you don't have a smartphone you can use, hit me up, I can get you something. All right, I've got extra phones I can wipe and give to you, but the college also has extra laptops they can lend out. So if you don't have a smartphone, I can get you a laptop from the college that you can use for the day, and we can do the Zoom thing on that.
I have a question about our work.
Sure.
So I know you said to take a picture, scan the free response questions, but does that mean you don't want us to send in our work for let's say the true or false questions or the multiple choice questions?
If you want to send me the work for the true, false, and multiple choice, you can, but I'm not going to grade it. So the true,
Got it.
false, and multiple choice are either right or wrong. Now I'll say this with a small caveat. If you've like done a meaningful amount of work for a multiple choice question and you think for whatever reason that like either the question has a typo, the correct answer isn't there, you're not going to get credit and it's not fair, by all means send me that work. Or if you think for whatever reason that like you're really stuck between two answers, you're like, this looks right, and here's the work I did that makes this look right, but that also looks right, and here's the work I did to make that look right. If you're in one of those deeply conflicted situations, definitely send me that work. In the last year, I think twice I've given partial credit on a true, false, or multiple choice question for reasons like that.
Okay.
But you're not required to. In general, I don't recommend it, but if you feel it necessary, you're compelled to for a reason, feel free. And if you do that, make a little note explaining why, and I'll look deeply into it. Any other questions about?
I have a question.
Sure.
All right. When it comes to like scanning our work, but we're using our phone for Zoom, can we still do that while we're on Zoom? Like, how does that work?
You can keep Zoom open while you scan. Yep. Obviously, the camera's going to be moving around. Generally, if you're done with the test, you've submitted the test, and you want to close Zoom to scan the work, I'll usually allow that. I have in the past. I'm a little like back and forth on it because obviously you could close Zoom and then do something sketchy. So the general rule is I want the scanned work in within like 10 minutes of when you submit the test. So if you want to close Zoom to scan the work, that's okay. If you want to leave it open while you scan the work, that's awesome, but I'm not going to beat you to death over it. So it is okay to close Zoom to scan your work. Other questions?
Do we have to let you know when we're gonna close Zoom, or should we just like end the meeting?
It's a good question. No, you can just end it. I've got the logs. So I check the logs afterwards to make sure that the written work is submitted within 15 minutes or 10 minutes of when you finish the test. I generally don't check the Zoom logs to see when you closed it. As long as, I guess I should, if you close Zoom before you submit the test, that would be sketchy. Usually people have asked, let's stick with that. Yeah, please let me know when you finish the test and let me know when you're going to leave Zoom. I would appreciate that. You can pop out of the breakout room. You can like leave the breakout room. You'll come back to the main session automatically, and you just say, hey, I'm done. I'm going to scan my work, and then you can bounce. That I would appreciate that just as a courtesy. Any other questions here?
And then you said if you're doing it at like the DRC or some testing center that we just do it by what they say and then scan the work in right after.
Exactly. Yeah, if you're taking the test at the DRC, then they will actually take your work from you, scan it and send a copy to me. So you don't need to do anything there. If you're at some other testing center, like you're out of the area, but you really don't want to deal with the hassle of the proctoring, if you would prefer to go to like a Pearson testing center or one of the other professional testing centers, a testing center at a university. I don't know if you guys know this, you can pay a fee to go take a test anywhere at a university or college. They all have testing centers. If you elect to do that, then you just have to follow their procedures. And then if that particular testing center doesn't scan the work for you, which our DRC does, then I would ask that you scan it and submit it yourself after the test. Just so I know, is there anybody considering doing that? Is there anybody who's not in Gainesville and is considering using a testing center to take the test, like a non-Santa Fe testing center? So you don't want to do the proctoring online. You're not using a Santa Fe testing center, you're using something else. Anybody in that situation? No. Okay, cool. All right, then I think we are done with the rules and procedures for exam 1. I'm going to let my cat out because he's tearing up the weather stripping, and we're going to get started talking about inverse functions. Or homework questions first, right? No, oh. You on? You got issues? Bring that. Well, now. Okay. So then I guess the first order of business in class proper is homework questions. Are there any of those?
I had one for homework 3. Is that posted yet? I didn't see it last time I checked, so I just wanted to.
It is
check.
up. Yeah, I got it up this morning.
Perfect. Thank you.
So any homework problems we want to see? Type them in the chat or just hold spacebar and let me know.
If you could do one of the combining functions with the domains. It was like one of the last 8 pointers on the homework.
Let's see.
I think homework number 2, number 57 is a domain.
Number 52.
All right, so I've got 52 and 57 from homework 2. Yep, I'd be happy to look at that. And 57 is one of our like combine and then find domains. Sure. Okay, any others?
58.
Okay, I can take like one of them.
12.
Homework 2, number 12. All right, let's start.
Yes, sir.
Let's get these done, and then if there are other burning ones, we can look at those. So homework 2, problem 12 is this guy. Kitty cat, I just tried to let you out. You didn't want to go out. I don't know what you need. You don't have to chill. Okay, so the graphs of the function f and g are shown. The function blank has greater average rate of change from 0 to 1. The function blank has greater average rate of change from 1 to 2. The functions f and g have the same average rate of change on what intervals? So let's look at the graph. This is homework 2, problem 12. Which function has greater average rate of change from 0 to 1 and from 1 to 2, right? Yeah. So I think it would be wise to approximate the average rate of change for each of these. From 0 to 1, let's see, it looks like g of 1 is a little bit smaller than 1, maybe exactly 1. So let's look at this first guy here. Let me bring this down. We'll do g first. G of 0 is what? Looking at this graph.
0.
0. And g of 1, again, looking at the blue graph here, g of 1 appears to be maybe exactly 1, right? Maybe a tiny bit less, but about 1. So the average rate of change for g from 0 to 1 is going to be g of 1 minus g of 0 divided by 1 minus 0. Right, that's the formula for average rate of change. So since g of 1 is 1, g of 0 is 0, this is 1 minus 0 over 1 minus 0, which is 1 over 1, which is 1. So it looks like the average rate of change for g from 0 to 1 is 1, or very close to that. This looks like it might be a tiny bit smaller than 1, but definitely at least 1. Very, very close to 1, I should say. On the other hand, f of 0, that's also 0. F of 1 though, look, f of 1 is bigger. F of 1 is maybe 1.5. I understand that these questions where you have to kind of estimate are a little bit frustrating. But if you think about just the slope, right? The slope of the line connecting 0, 0 to the point on the graph here, or the point on the graph here, you can see right away that the f slope will be bigger. But now that we know this, we can go ahead and do the computation here also. So the average rate of change, this takes to write, for f, again, this is just from 0 to 1, is f of 1 minus f of 0 over 1 minus 0. We said f of 1 is about 1.5 and f of 0 is 0. So this numerator is 1.5 minus 0, and the denominator is still 1 minus 0. So that's 1.5 over 1, which is 1.5. So if you want to be kind of quantitative about it, right, if you want numbers you can compare, we can actually estimate these average rates of change pretty well. So from 0 to 1, f of x has the greater rate of change. From x equals 1 to x equals 2, we're going to do something similar, but let's just take a look and see if we can reason our way to it. First off, where is 2 on the horizontal axis here? Is it
The fourth line.
Good, right? Because each tick mark here, there's 2 tick marks to get to 1, so each tick mark is 1/2 or 0.5. So this is 0.5, or 1/2, 1, 1.5, or 1.5, and then 2. Now we're looking from x equals 1 to x equals 2. So what I would need, in addition to the stuff that I already have, is f of 2 and g of 2, because I already have good estimates for f of 1 and g of 1. Let's look at f first. We did g first last time. Let's look at g first. G of 2 is the y value up here. So what is that? That's like this tick mark. So that's 1, 2, 3, 4. G of 2 looks like it's about 4. And we saw earlier that G of 1, oh, sorry, I'm writing in a place you guys can't see, aren't I? We saw earlier that G of 1 is about 1. So, you know, G of 1 is 1, G of 2 is 4, or at least very close to those. So the average rate of change here, I'm not going to write the words, G of 2 minus G of 1 over 2 minus 1 would be 4 minus 1 over 2 minus 1, which is 3 over 1, 3. So for the function g, the average rate of change from x equals 1 to x equals 2 is 3. What about the function f? Earlier we said f of 1 is a little bigger, right? It's like 1.5. F of 2, if I come out to x equals 2 on the graph right here, f of 2 is the y value here, which looks like it's maybe 3. Right? It's a little bit smaller, definitely smaller than the y value on the g graph. Looks like it's smaller by about 1. So f of 1 is 1.5, f of 2 is about 3. So the average rate of change for f from x equals 1 to x equals 2 would be f of 2 minus f of 1 divided by 2 minus 1. The denominator there is 1, of course. F of 2, we said is 3. F of 1, we said is about 1.5. So 3 minus 1.5 is 1.5. 1.5 over 1, which is 1.5. And I'd like to point something out. What kind of function is f?
Constant.
It's not constant. Remember, a constant function, that's like a horizontal line.
Slow.
Linear.
Linear.
Linear. And I think I know what you were getting at. It's that the rate of change is constant, right? The rate of change is always 1.5 because f is a linear function and its slope is 1.5. So the rate of change for f, we could have deduced without doing this calculation that the rate of change from 1 to 2 has to be the same as the rate of change from 0 to 1 because f is a linear function. But we've now answered the second question, right? From x equals 1 to x equals 2, who has the greater rate of change? G does. So basically the idea is that the function g kind of starts off growing slowly. If you look down here at slopes, if you kind of imagine someone skiing along this graph or something called a tangent line, the skis would have would be like lower sloped here and then getting bigger and bigger and bigger. So the rates of change for g are getting larger and larger. The rate of change for f is constant. So no matter where you look, the rate of change for f is always 1.5. But for g down here, the rate of change is smaller. It's like 1. But for g over here, the rate of change has grown to like 3. So the first guy there would be f. The second guy there would be g. And you could do that kind of qualitatively, like I just said, just kind of thinking about slopes rather than going through the calculation. The calculation is the way to be sure. Finally, they ask us for an interval along which these functions have the same rate of change. Any guesses as to that?
0 and
1.5.
1.5.
Excellent, Bianca. Yeah, exactly. We're looking for an interval where the slope of the secant line is the same for those two functions. And if you have two functions whose graphs touch twice, like we have here, right? These graphs touch over here, and then they touch again over here. The secant line between this x value and this x value are necessarily the same because the points are the same, right? It's kind of cool. So the average rate of change for f and g from 0 to 1.5 is the same. Because if you kind of think about the height that they've both gone over the width that they've both gone, since they touch at this point and touch at this point, the height and the width are both the same. And the rate of change is the height divided by the width, the rise over the run. So yeah, finally. Rate of change x equals 0 to x equals 1.5 must be the same for f. Now, since g's rate of change is always getting bigger and bigger, there actually couldn't be another interval over which they have the same rate of change. F's rate of change is bigger until you get to 1.5, and then g's rate of change is bigger everywhere thereafter. So that's not only a solution, it's the unique solution, and that's kind of a cool thing too. All right. Any further questions on this fella? Calculations we did, formulas we're using, any of that? Okay, let's move to the next problem then. The next one, if we're going in order, I think is 52. Some differential equations from there. All right. So from the graphs, they want us to give them f plus g of 7, f minus g of 7, f times g of 7, and f over g of 7. The graph, giving us the whole graph here is big overkill. I only need 2 function values. So, number 2, problem 52, find plus g of 7, minus g of 7, times g of 7, over g. So, does anybody remember, I mentioned that there's a kind of trick to doing these problems. There's a place you need to start, and if you start at that place, kind of everything else will unfold nicely. Does anybody remember that sort of starting place for these problems?
Writing it out.
Yeah, we got to write out the definition of the thing that's being asked for. So let's start with f plus g of 7. If I want to take that first step, I think I called it like a schematic step or a descriptive step, definition step. What is the definition or schematic for f plus g of 7?
F of 7 plus g of 7.
Perfect. Yeah, this is f of 7 plus g of 7. That's the definition. That's the definition of the sum function. And this, you would do this for any x here. If you had a variable x here, you would write f of x plus g of x. If you had any other number here, you would write f of that number plus g of that number. If you had dog shit here, you'd write f of dog shit plus g of dog shit. So I look on the graph, I need to find f of 7, and I need to find g of 7. Now remember from section 2.1, f of 7 is the y value on the graph of f associated with the x value 7. So let's look at our x-axis here and see if we can find 7. 1, 2, 3, 4, 5, and this is marked as 5. So yeah, each tick mark here is 1. So 7 should be 2 to the right of 5. So this is x equals 5, x equals 6, x equals 7. F of 7, now I'm looking on the blue graph because we're talking about the f function. F of 7 is going to be the y value here. Right, the y value on the blue graph whose x value is 7. So that point. That point there is 7 comma something. What's the something? Well, if each tick mark here is 1, 2, 3, 4, 5, yeah, each tick mark here is 1. So when I come out to 7, I come down to my graph here. F of 7 is this y value, which is -3. So I'll write it over here. F of 7 equals -3. Are we all clear on where this is coming from?
Yes.
Alrighty. Then the other thing I need is g of 7. So again, I come out here 5, 6, 7. I go to the graph of g. The y value on the graph of g is, looks like 1, 2, +3. So g of 7 is +3. And it turns out this is all we need from the graph to answer every one of these. So f plus g of 7 is f of 7 plus g of 7, and we just found both of those. F of 7 is -3, g of 7 is +3, and when you add those two together, you get 0. So f plus g of 7 is 0. What about f minus g of 7? Well, that would be f of 7 minus g of 7. F of 7 is still -3, minus g of 7 is +3. So that's -3 minus 3, which is -6. And we'll continue like this. F times g of 7, by definition, is f of 7 times g of 7. I'm going to use some of the space over here. So that's -3 times +3, which is -9. And then lastly, f over g of 7 is by definition f of 7 over g of 7, which would be negative 3 divided by positive 3, which is negative 1. So it really is the case that the magic step for these is just knowing the definitions, kind of knowing to write it out, getting comfy with the notation, really. Any questions about this? Sorry, my vet just texted. All righty, then we're going to move to the next one, which was 57. 57, 58, then we're going to talk about inverse functions. I may have to pull the plug after 57 just to make sure we have enough time. But if you want to see 58, you come by office hours. We'll see how quickly this goes. All right. So we want to find all these combinations and their domains. 58 is the same thing. Tell you what, let's do a quick vote. If you want to see 57, give me a thumbs up react here in Zoom. Got 3. And thumbs up react if you want to see 57 over 58.
Either one is fine.
So I think we got 4 unique reacts there. 58, give me a thumbs up or a hand raise, something like that if you want to see 58 in place of 57, more than 57. A few more seconds, 1 so far. All right, 57s have it. I think the algebra steps in 58 for simplifying is a little bit harder, but the domain in 57 is a little tougher. Let's do it. So I'm going to just write this down. 2. Question 57. Find all the combinations. And domains. F of x is the square root of 25 minus x squared. Let's be clear just for a fun second. This is not the same thing as 5 minus x. You can never, ever, 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 ever distribute square roots over addition or subtraction. So we've got to just leave it like that. Common mistake. And g of x is the square root of x plus 2. Which similarly is not the square root of x plus the square root of 2. All right, so f plus g, f minus g, f times g, f over g, and their domains. Here we go. F plus g is f of x plus g of x, which is the square root of 25 minus x squared plus the square root of x plus 2. And there's nothing more we can do with this because of your order of operations, right? Your order of operations tells you that you can't actually put these together into one square root because they're being added here. The square root is a power. Remember, it's the 1/2 power, and that comes before addition in your order of operations. So there's no simplification that can be done here. This is just what it is. But then to find the domain, we need to think about the relevant red flags. The red flags are the variable stuff under the square root. So on the one hand, we need 25 minus x squared to be greater than or equal to 0 from the first square root.
I have a question.
Yes, ma'am.
So the square root and the square doesn't cancel out?
No, because there's 2 terms here separated by subtraction. So if this was just the square root of 25 or just the square root of x squared, then you could simplify like that. All right, the square root of x squared on its own, that is x, or absolute value of x. The powers would cancel. But because here, these are being subtracted, again, it's an order of operations thing. If you think about what you have to do here, if you wanted to evaluate this, you'd have to square it, then subtract it from 25, then take the square root. and that the order of operations there doesn't let you take the square root before you subtract, right? The square root is like this is like a parentheses thing. It's like paren 25 minus x squared, all to the 1/2 power. So your first thing would be to do the power, then the parens, then the square root.
Yeah. Okay.
It's a little bit wonky, but the order of operation stuff really is the way to kind of think about whether you can simplify something. So that's a good question. I'm glad you asked. Let's come back to the domain now, though. How do I solve this inequality? Who remembers?
The x itself.
Leave the x alone.
It's a perfect square.
It's true, this is a perfect square.
So you factor it out.
Very
Equal
good.
to 0.
Yeah, so we're gonna factor. We factor this as 5 minus x times 5 plus x, and it's greater than or equal to 0, still there. Thank you. So after we've factored, we figure out where these things are equal to 0, and we make a sign chart or a number line. So from this piece, I get x equals 5. From this piece, I get x equals minus 5. And I make a number line. I'll put minus 5 here, 5 here. And then this creates 3 regions. From each region, I test a point in the inequality. So over here, if I test x equals -6, if I plug -6 into this inequality, do I get a true statement or not? Well, it's 25 minus -6 squared. -6 squared, here's what I get when I plug into the inequality to test. -6 squared is positive 36. So 25 minus 36 is greater than or equal to 0. Is that true? No, because 36 is bigger than 25. When I subtract these, I get what, -11? This is -11 is greater than or equal to 0, which is not true. A false statement. So this region is out. In the middle region, I can test x equals 0. And there I'll have 25 minus 0 squared is greater than or equal to 0. 0 squared is 0, so this is 25 is greater than or equal to 0. That's a true statement. So this region is good. And then to the right of 5, I can test x equals 6, and I'll get the same thing I got over here. We've got 25 minus 6 squared is greater than or equal to 0. That's 25 minus 36 is greater than or equal to 0, which is -11 is greater than or equal to 0, which is false. So this is out. So the first guy tells me that my domain can't be any bigger than -5 to 5. Just from this first square root, I can only plug stuff in that's between -5 and 5. Your quiz has a few problems that are just inequalities like this, and I want you to really pay attention to how to solve them. This is considered preliminary material. This is considered material that you're supposed to know coming into the class, although I suspect that not everybody has seen a good treatment of nonlinear inequalities. So I'll remind you, like we did on the day we talked about this before, this is in the textbook in section 1.8. And if you're rusty on this, go back into the book and look at some problems from 1.8. As you go through the quiz, take those problems seriously and make sure you're comfy with them, because this tool is something we're going to use all semester long. The other domain thing, we need x plus 2 to be greater than or equal to 0 as well, because there's a square root with x plus 2 underneath it. Now, this is a linear inequality. There's no like x squareds or anything weird like that. This function over here, x plus 2, is a linear function, so we call this a linear inequality. And these are much easier. You can just solve these by moving things around. So if I subtract 2 from both sides, I get x is greater than or equal to -2. And I can put that on a number line right away. Here's -2. And I want everything greater than or equal to that. So that's this stuff. If I take this solution set here and put it on a number line, I didn't do that explicitly before, sorry. we had everything between -5 and +5. And we're using brackets here because we have a greater than or equal to. It's okay if x is equal to 5 or -5. All right. I want to kind of pause for a minute and ask, is everybody comfy with where we're getting each of these two little individual domains?
Yes.
I'm confused on why you plugged in 6 and -6.
So the way that these nonlinear inequalities work, inequalities like this where the function isn't a linear function, we have to factor them, find the numbers where this thing is equal to 0 or undefined, any place where the top or bottom is 0, put those on a number line, and then test a point from each region. So the -6 and +6, that's me testing to see if this region is a part of the solution. So after we kind of chop up our number line, we have to take a point from each of the chopped up regions and test that number in the inequality. If when you plug in that number, the inequality is true or satisfied, then that whole region is a part of the solution. If it's not true when you plug in that number, right, like here, we got -11 is greater than or equal to 0, that's false, then that whole region is kicked out of your solution. So it's kind of nice. This says that like if one point in one of those regions works, then every point in that region works. And if one point in that region doesn't work, then no points in that region work. It comes from continuity. We're going to talk about something called the intermediate value theorem later, but the fact that the function we're working with here is continuous, that's what guarantees this works. But yeah, these are test points. Each one of these is a test point. You have to test one point from each region. All right. So let's keep moving. I want the domain of my whole function. And my whole function is these two things added up. So I need to have this guy's domain satisfied and this guy's domain satisfied. So what I'm looking for is the overlap between this set, which is -2 to infinity, and this set, which is -5 to 5. So the domain of f is what's called the intersection another word for that is the overlap of the two intervals. That overlap, if you wanted to write it in interval notation, would be -5 to 5 intersected with -2 to infinity. But the easy way to figure out what this actually is, because this is, nobody wants to write their answer like this, intersections are kind of ugly to put in your interval notation, is to put them both on the same number line. So I'm going to shade one of these, the -2 to infinity, I'll shade in teal here. And the -5 to 5, I will shade in black. And remember, I'm looking for the overlap. So this intersection is asking what's common to both of these. That's what this symbol means. You're going to take the stuff in here, the stuff in here, and see what is common to both of them. It's the middle of the Venn diagram. So what's my domain?
-2, 5.
Excellent. It's the closed interval from -2 to 5. That's the stuff that is common to both of these. That's the stuff here you see that is shaded in both black and blue. Alrighty. So I know some of this set theoretic stuff is something that you may have not been pushed on too hard in the past. They may have just said it in class and then not tested you on it. But here, problems like these, they're required. That's just the first one, but the good news is the other shit's going to go really fast, because just like when we did this in class the other day, it's like, oh, the same red flags, same red flags. So let's look at f minus g, f times g, So I'll just do this in our domain. -2 to 5. And you may remember me using that intersection notation yesterday when, or I guess it was Tuesday when we introduced this. So f minus g, that's f of x minus g of x, which is the difference of the square roots. What's my domain for f minus g? Don't try to recalculate it, kind of think in context.
The same.
It's the same thing, right? We got the exact same red flags in the exact same places. The only difference is the plus between them is now a minus, and that had no effect on the domain. Now, there are some of these where things will change a bit. Let's look at f times g. This would be the square root of 25 minus x squared times the square root of x plus 2. And in this case, it is possible to combine these algebraically. It's true, rule, that the square root of a times the square root of b is actually equal to the square root of ab. You multiply two square roots. You can write that as a single square root with the product inside. But you need to use parentheses here, of course. Do you think this changes the domain? If this is equal to this, is it possible for this function to have a different domain than the previous two?
No.
Very good, very good. Because again, a plus between them, a minus between them, a multiplication between them. These things all have the same domain red flags coming from the same exact place. So the domain again here. And you may recall when we introduced the combinations of functions, we said these three all have the exact same domain roots. Always the domain of one intersected with the domain of the other. The next one can get slightly more complicated because you have to make sure the bottom isn't 0. So for our next guy, we have the square root, it's f of x over g of x, right? F over g of x is f of x over g of x. It's always how we get started. And f and g still the square roots that we're looking at. So root 25 minus x squared divided by root x plus 2. And if you wanted, I'll say one more time, if you wanted here, you could write this as a square root of that ratio. That does work. The rule, it's kind of a similar rule. Square root of a over the square root of b. It's the same thing as the square root of a over b. Going from here to here, the kind of two different forms, that doesn't change the domain because these things are equal. But does this have any red flags that the previous three didn't?
It has something downstairs, so you would change the bracket to parentheses for -2, and then make 5 for the bracket.
Very, very good. So the new red flag here is the square root of x plus 2 downstairs. Or if you want to think of it as this guy, you could say it's just x plus 2 downstairs, all under one big square root. So we need square root x plus 2 to not be equal to 0. And we know that the square root of x plus 2 is equal to 0 only when x plus 2 is equal to 0. You square both sides, and 0 squared is 0. So that's true only when x is equal to -2. So we need this thing to not be 0. The only time that thing is 0 is when x is -2. So exactly like Ainsley said, we're going to take the domain from last time because we still have those old red flags. And we're just going to throw out the -2. I still, in order to make sure that the stuff under the square roots is non-negative, I have to stay between -2 and 5. That's what we established in the first part. So that's where the -2 to 5 endpoints come from. But then in addition to that, I need to make sure the bottom isn't 0. And the bottom would be 0 when x is equal to -2. So -2 was in all of these previous domains. That's what the bracket on the left means. So here we need to kick out -2. Because -2 would make the bottom 0. If you take this set, -2 to 5, and you kick out -2, you get this set. We comfy with the notation? I should say questions about the notation.
No.
I'm good. Okay. Those were all the combinations they wanted, right? Yeah, all right. I'll say that this one, the algebra here is a little bit subtle, and I strongly encourage you, especially when it comes to this last one. I'll just say a little comment. Finding domains. Combinations of f and g. First, write down the function. Second, don't simplify before finding the domain. So kind of like I said in the previous ones, like stop here to find your domain. Stop here to find your domain. Don't try to like cancel or flip anything. Don't cancel or flip anything. Don't try to simplify. You'll lose information when you do that. Then you look for red flags. In other words, you want to look for those red flags in the non-simplified version. Specifically when you have like ratios like this, and you have a function like this with variable stuff downstairs, when you divide by 1, you're going to end up flipping when you simplify. That's going to bring this x upstairs. We're going to bring this x plus 7 upstairs. So use your non-simplified version to find the domain, then simplify. That is how you avoid the pitfalls there. All right, if you want to see 58 come to office hours, we got to talk about some other stuff. That text. So, one-to-one functions and inverses. What we want to do is find a way to exactly undo a function. So the definition the inverse of a function f is another function called f with a -1 up here. We read this as f inverse, and it has nothing to do with the power. I know that notation is confusing, but it's just the notation that mathematicians have chosen over the years. This is not a power. We mean f inverse in the sense that I'm about to describe, which exactly undoes function f. That is. All right. Let me describe a function to you. In the morning, I wake up and put on socks and shoes. So I have the socks and shoes machine. That's a function. It takes as its input my foot, and then I put on the sock, and then I put on the shoe. And the output is a clothed foot. If I want to invert that function, I need to take off the shoe and take off the sock. That would be like a composition. So what we want to do is take x and do f to it. That's f of x. Right? That's the output you get from the function f applied to the input x. And then I want to undo that. The way you do that is by taking the inverse of that thing. So the sense in which we say f inverse undoes f is that if you compose f with f inverse, you get the thing back that you started with. The other notation for this is f inverse circ f of x is equal to x. And we want it to be the case that if you do it in the other order, everything works out too. This is the definition of an inverse function. If I give you two functions and I ask you, are they inverses of each other? I want you to plug one into the other and see if you get just x out. And you need to try it both ways. There are such things as left inverses and right inverses, where like this first one works, but the second one doesn't. We're not interested in those in this class. We need to make sure it works both ways. So this is your definition. But the intuition is that the inverse function should be the one that exactly undoes the original one. So for example, just do this in words. If f is the function which takes x, multiplies by 2, then adds 5 to the result, find f inverse. Okay. So what I want to do, I know what f does. F takes a number, multiplies it by 2, and then takes that thing and adds 5. Sure, I could write down an algebra formula for f, but that's not what I'm trying to do. I want to find in words the description of the inverse function, the function that exactly undoes that procedure. So think about the socks and shoes. I put on my socks, then I put on my shoes. That's the original function. The inverse function is not take off socks, take off shoes. I can't take off my socks before I take off my shoes. I have to take the shoes off first. So the inverse function is the function that undoes each operation of the original in the reverse order of the original. So here, f inverse must take its input, whatever, x, and then I need to undo these two operations in reverse order. So the very last thing that f did was add 5. So this guy must and then subtract 5 first. So the original function multiply by 2, then add 5. The inverse function is going to start by subtracting 5, and then how do I undo multiply by 2?
You divide by 2?
Exactly. Then we divide the result by 2. Okay, that's it. I found the verbal description of f inverse, given the verbal description of f. And you can always do this, as long as the original function is a one-to-one function. I'm going to describe what one-to-one functions are in just a second. Before I do that, though, I want to write down the algebraic form of these and verify that this is true. All right, so verify algebra. The formula for the function f of x, the function that multiplies by 2, then adds 5, well, you multiply x by 2, and then you add 5 to the result. Again, we got to really be thinking about order of operations here. The algebra formula for the thing we think is f inverse, that's going to take x, subtract 5. So f inverse of x takes x, subtracts 5, and then divides that whole result by 2. And the question is, if I check that those functions satisfy this definition, will I get a true statement? So let's go ahead and compose. Checking that f inverse of f of x comes out to x. Well, remember how to do this. Start from the inside, right? This is just like the problems we were doing the other day, where you got to plug into the inside and then plug that into the outside. This is f inverse of, what was f? It was 2x plus 5. That's why function notation is so damn important. Everybody with me so far up to here? We all see why we can go from this to this? Because this thing right here is 2x plus 5. F of x is 2x plus 5. And now f inverse has formula this. So whatever I plug into f inverse, I just plug in here, right? F inverse of dog shit would be dog shit minus 5 all over 2. F inverse of pi would be pi minus 5 all over 2. So f inverse of 2x plus 5 is 2x plus 5 minus 5 all over 2. And I would say normally you should do this in parentheses, because maybe there's a power here or a number here that you'd have to distribute. And now if we simplify this, 2x plus 5 minus 5, there is no power, there is no number to distribute. So we can just treat this as 2x plus 5 minus 5. That's 2x over 2. And hey, what do you know? That really does just come out to x. And if we compose in the other order, you gotta check both. This would be f of, what is f inverse? It's x minus 5 over 2. Now what does the f function do? F of anything is 2 times that thing plus 5. So f of this is 2 times this plus 5. Now this is 2 over 1 times x minus 5 over 2. The 2's will cancel. You get x minus 5 plus 5, and that is indeed x. So you can come up with your inverse function verbally. If you have a verbal description of the original, you can get a verbal description of the inverse by undoing each operation in the reverse order, just like the socks and shoes. Socks go on, shoes go on, shoes come off, socks come off, in that order. But most of the time, this is an algebra class, we want to do things algebraically. in order to know you're in a situation where you're allowed to do things like this, we need to talk about a theorem. We need to talk about what it means to be one-to-one and when we can guarantee the existence of an inverse. So let's say fact is a theorem. A function f has an inverse function if and only if f is 1, 2, 1. What does it mean to be one-to-one? Function, make sure you're writing this down. A function f is 1 to 1 if there's a handful of ways to say it. Different inputs lead to different outputs. That's the verbal way to say it. Meaning, if I take two different inputs, two different x values, they won't both get sent to the same y value. They have to get sent to different y values. It's kind of like the definition of a function in reverse. And you can see why that may be the case, because this is the condition that guarantees the existence of an inverse function. But this is what we mean. So definition of a one-to-one function. Function f is 1 to 1 if different inputs lead to different outputs. In terms of the algebra, you would say if x is not equal to y, then f of x must be not equal to f of y, right? If you look at two different inputs, they got to go to two different outputs. The contrapositive of which is if f of x is equal to f of y, if you have two outputs which are the same, then those inputs actually better be the same. You must actually be looking at the same input. In practice, how do we usually do this? Horizontal line test. Let me write it like this. The graph of f passes the horizontal line test. And I'll explain what that is. But just want to be clear what a one-to-one function is. Here's a picture. This is the function f in a mapping diagram. This is not the horizontal line test. So picture explaining what we're doing when we find the inverse operation, the inverse function, is we're finding the new guy that sends all the outputs back to the inputs from which they came. And that new guy won't be a function. So here f is 1 to 1. So f inverse is a function. I can always draw the arrows going back the other way, but the result might not be a function. This is the good case. Here's the bad case. I have two different inputs, x and y, and they both get sent to the same guy over here in the range. This is where f of x is equal to f of y. So here you see x and y are distinct. X is not equal to y, but the function f maps those two distinct inputs, oh shit, to the same output. It's bad. So what would the inverse operation look like here? Well, it would have to send this guy back here, and it would have to send this guy back here. This would be f inverse. Let's just call this z. Let's say that object in the output, in the range there, is z. Here, f inverse of z, f inverse has to send this guy back to the guys from which he came. But that means he has to be both x and f inverse of z has to be y. Think back to your very first homework. If x and y are two different numbers, is it possible for a function to take a single input back to two different outputs?
Oh,
No, right? That's the very definition of a function, is that each input has to go to one and only one output. So if you take a function that's not one-to-one, like the black function here is not one-to-one because it takes these two different inputs to the same output, then the relation that sends those outputs back to the inputs from which they came has to fork this guy. So the outputs for f are inputs for f inverse. And this particular input for f inverse would get sent to both y and x, which are distinct objects in the domain. So this is not allowed. Here, f inverse would not be a function. You can always take your mapping diagram and point the arrows back the other way. There's always what's called an inverse relation. But what we want is for that inverse relation to be a function. So if you look at the black here, this is a function. The black is a function here. Each input goes to one and only one output. The black here is also a function. Each input is only going to one output. But here, if you turn those arrows back the other way, you still get a function. Here, if you turn those arrows back the other way, the blue here is not a function. And that's what we mean when we say here, f is not one-to-one. The intuitive thing is that the inverse sends each output back to the input from which it came. So if f sends Joe to Sally, then f inverse sends Sally back to Joe. If f of 3 is 7, then f inverse of 7 has to be 3. If you have two different inputs or more than two different inputs going to the same output, then the inverse relation, the inverse mapping, is going to have to send that one output back to all those different inputs. And that's not something functions are allowed to do. So one-to-one functions are the only guys that have inverse functions. A function here, where each one input goes to one and only one output, is called a one-to-one function. Does anybody want to guess what you would call this in that same language where you've got 1, 2 inputs going to one function?
2-to-1.
2-to-1, perfect. This is a 2-to-1 function. Can anybody think of any 2-to-1 functions you know in your algebra experience? Any functions that send, so for every output, there's two different inputs that go to it.
Y equals 5.
A 5 is like an infinity.
Would you say like a parabola? Like
Yeah,
a
yeah,
absolute
yeah.
value type of thing?
I heard 2 or 3 correct answers in there. A parabola, x squared. Think about x squared. -1 gets mapped to 1, +1 gets mapped to 1. So 1 gets hit by 2 inputs. That's a 2-to-1 mapping. -2 gets mapped to 4, +2 gets mapped to 4. That's a 2-to-1 mapping. With the exception of 0, x squared is a 2-to-1 function. And there are functions that are much worse. I think it was Mason said like y equals 5 or f of x equals 5, a constant function. Every single input gets mapped to the same output. That's an infinity-to-1 function.
Would you say absolute value?
Absolute value is a 2-to-1. Yeah, very good. 3-to-1 functions, 4-to-1 functions, infinity-to-1 functions, they all exist. But the ones we want when we're talking about inverses are 1-to-1 functions, because those are the only guys where you can undo that mapping. This is very useful in cryptography, by the way. If your cryptographic function needs to be 1-to-1 in order for someone on the other side who has the inverse cryptographic function to undo it and get a distinct message. If it's not 1-to-1, if the crypto function isn't 1-to-1, then there's no way to undo it and know what the message is, because this letter could have been an A or it could have been a B. We don't know. All right, horizontal line test. So you got a function, you want to know if it's 1-to-1, graph it. Graph that function. Here's what it says. If any horizontal line hits the graph of f more than once, then f is not 1-to-1. So it's more like a test to see if something isn't 1-to-1 than a test to see if something is 1-to-1. For example, what do we say? X squared. If I draw in here the horizontal line y equals 4, for example, you could use lots of other ones, it hits the graph twice. If any horizontal line hit the graph more than once, automatically not 1-to-1. But we can see why if you want to think about it carefully. It's because both -2 and +2 get mapped up to the y value or the output 4. So this is a 2-to-1 function everywhere except 0. At 0, it's actually 1-to-1, but that's boring, right? You don't want, a function is not one point. You need like a graph. You need more shit than that. Another example. About.
I have a question, Professor.
Yeah, sure, go ahead.
So for the exam for graphing, will those most likely be like the free response where we have a specific answer, but you want us to see the graph on our paper?
There will be questions where I ask you to draw a graph, and those will be free response questions. There will also be questions where I give you a graph, or I ask you questions about graphs. But the ones where you're explicitly required to draw a graph will definitely be free response. Is that what you're asking?
Yeah, I didn't know like what we should put in the like the answer box. If something just says like, is it going to just say do the graph, or is it going to say, okay, draw this graph and then answer this question?
Yeah, it'll be a draw the graph and then answer some question with the graph. Or, you know, maybe I'll ask you to draw a graph and like tell me what are the maxes, what are the mins. So on the paper, I'd want to see your graph, mins and maxes labeled, and then in the box, you'll type like the min is blank and it occurs at blank. So there will be very, very clear directions on each free response question saying like, this is what I want on your paper and this is what I need in the box. But yeah, good question. All right, here's another graph. This is the graph of 1/x. It's one of our parent functions. We need to know this one. Is this 1-to-1?
Yes.
It is, yeah, because no matter where I drop my horizontal line, it's going to hit this thing at most once. All right, you gotta think about a bunch of horizontal lines. So think about moving the horizontal line up and down. This one is one-to-one. Because no matter where you put that horizontal line, it's going to hit the graph at most once. Is there any horizontal line that never hits this graph?
X equals 0?
Or y equals 0. Yeah.
Y equals 0.
Yep, y equals 0. This horizontal line, x equals 0 is a vertical line. But y equals 0, the x-axis, this graph never touches it, right? It kind of approaches it as we go out here, and it approaches it as we go out here, but never touches it. Does that violate the horizontal line test? If there exists a line that the graph never hits, does that contradict this?
No.
No, that's fine. Yeah, that's fine. That's still not a line that hits the graph more than once. Right, so a line that the graph never hits, that's fine. All right, that's the horizontal line test. If your graph gets hit more than once by any horizontal line, automatically not one-to-one. And here you can see the explicit example, right, that f of -2 is equal to 4, f of +2 is equal to 4. So you've got two different outputs. Going to the same input. The two outputs are -2 and 2. Going to the same, sorry, two different inputs. Going to the same output, namely 4. All right. One-to-one functions have inverse functions. Non-one-to-one functions don't have inverse functions, unless you restrict their domain. Can we restrict the domain? Of f of x equals x squared to make it one-to-one? In other words, is there a way for me to throw away part of this graph so that's what's left does pass the horizontal line test? Here's f of x equals x squared restricted to x being greater than or equal to 0. Or f of x equals x squared restricted to x is less than or equal to 0. If I restrict the domain here, in other words, I'm restricting to 0 to infinity. Here I'm restricting to -infinity 0. If I restrict the domain of a non-one-to-one function, maybe I can make it one-to-one by throwing away the piece that makes it non-one-to-one. And usually there's multiple choices. This is an important idea, especially when you talk about trig functions. You guys are going to be learning about inverse trig functions at some point, presumably you're in pre-calculus. Trig functions are periodic. They're definitely not one-to-one. None of them are one-to-one. But we really like our inverse trig function, especially the tangent function. Inverse tangent, fucking awesome. So this idea of kind of throwing away part of the graph and keeping some of it, as long as that some of it is one-to-one so that we can work with that, that's a big deal. So maybe we could find inverses for each of these. The clock on my computer isn't correct. I think I am already 6 minutes over, but I want to, and I apologize in advance. If you've got to go, you've got to go. The video will be up on YouTube later today. I need to show you how to find an inverse function algebraically. And I want to talk for a second about symmetries. So this is going to take a second, but please bear with me just a tiny bit longer. Restricted domains can give you one-to-one functions from functions that are not one-to-one. Some functions just are one-to-one. How do you find the inverse? Whether you're restricting the domain or not. We talked about how to do it verbally. That was the very first thing we did. But you also need to know how to do it algebraically. You're assuming f is one-to-one. Well, actually, no, I'll bake a step in here. So your first step is to write y for f of x. All right, so you've got like f of x equals some stuff. Instead of that, write y equals some stuff. Then solve the equation for x. So you write y equals, whatever, x squared plus 7. Solve that equation for x. So you get x equals, the square root of y minus 7 or something. Then you need to consider any domain restrictions. So if you restricted the domain to make your function one-to-one, there's going to be a choice element as you solve for x. Like you'll take a square root and you'll get a plus and minus. You need to pick the plus or the minus that matches your choice of domain restriction. I'll show you an example in a minute. And then the very last couple steps here, swap x and y. I strongly recommend you do this after doing these. I know some people learn to do this first. That's not the right way to do it, because when you have to consider your domain restrictions, you're going to get confused. Saving this for after this will help you with the domain stuff. And then that's it. Then that's it. 5. Having done this, y is now f inverse of x. All right, so let's look at an example. Yeah, we can do, screw it, yeah, easy one first, right? Find f inverse f of x. 3x minus 2. It's an example from your book. Your book, by the way, also suggests doing it in this order, right? Solve for x, then swap. It's an important distinction. So step 1, write y equals 3x minus 2. Step 2, solve the equation for x. So y plus 2 equals 3x. It's just adding the 2. And then divide both sides by 3. Y plus 2 all over 3 is equal to x. I have solved for x. 3, consider any domain restrictions. This function, no domain restriction here. The original function, 3x minus 2, you know what that looks like. It's a line. Slope 3, y-intercept 2, negative 2. Looks like this, right? And that is a one-to-one function. 4, swap x and y. So I'll have x plus 2 over 3 is equal to y. And then 5, having done this, y is equal to f inverse. So I'll write the f inverse on the left. F inverse of x is x plus 2 over 3. That's how this goes. One life is easy, right? The solving, the equation solving here can be hard. Figuring out the domain thing can be hard, but the procedure, this procedure works great. It's the way you do it. Okay. Let me show you a more complicated example. One where we have some domain restrictions. You know the graph of x minus 1 quantity squared? Let's say translate of x squared. I bring x squared to the right 1 unit, and that'll get me this. Is this 1-to-1?
No.
No, it's not, right? But if I chop off this half, or if I chop off this half, then the result will be 1-to-1. So I have to choose. I have to choose my domain restriction, and that's going to lead to a choice in the equation solving between a plus and a minus. Suppose I choose this guy. I'm going to hold on to this piece. Everything over here. I'll tell you my rule. I like to choose the domain restriction that includes 0. Right, so if I took 1 to infinity, that wouldn't include 0. But if I take negative infinity to 1, that does include 0. It's just a personal thing. But you're allowed to choose the domain restriction you want. So I'm going to take this guy. And on that domain, I will find the inverse. First, write y in place of f of x. Second, solve for x. So y equals x minus 1 quantity squared. That's equivalent to saying plus and minus the square root of y is equal to x minus 1. Right, take square roots on both sides. You need to use the plus and minus when you do this. Then I add 1 to both sides. Write it like this. If you had swapped x and y at the start, now you would run into a problem. You need to pick the plus or the minus that matches your domain. Here, this square root of y, this is positive, and it's going to, be big sometimes. It's going to be 0 sometimes. It's never going to be negative. So I've got 1 plus that, or 1 minus that is equal to x. Look at the part of the graph that I've preserved, this part. Are my x values on that graph always positive?